Okay, so the talk I'm going to present now is basically the evaluation of our runs driven by era interim. This is not just it's not. I'm not the main author. The main author of this study is Nicolina Van, who is now at Innsbruck University, and this is not just the runs from EUCP, but also from Cortex FPS. So there's a lot of people involved in this project. The main idea is basically that we have these simulations run at the kilometer scale, in which we basically turn off the parameterization of deep convection. Right? This is the first model intercomparison in which we can test the ability of a big ensemble of models on how they behave on that. So I'm going to present the results focused on an alpine area. We have a total of 22 simulations from 21 research centers, 6 different models, and the simulations are run at around 3 kilometers, more or less. And then we compare them against their 12-kilometer counterparts that use parameterized deep convection. So it's 10 years of simulation driven by era interim. So the simulations are driven by the same large-scale fields, and we are going to focus mainly on precipitation statistics. This is the description of the domain, well, the visualization. So basically you have the 6 models here. Can you see my thing, right? Yeah. So you have the 6 models here. We take the fields from era interim, we put them in a 12-kilometer simulation with deep convection parameterized, and then the groups tend to move from this 12-kilometer convection parameterized model to the 2 to 3 kilometer, in which deep convection is resolved by, well, or is permitted by the model dynamics. Okay, so there are these 2 differences, the resolution and the treatment of convection. This is what you get when you look at daily precipitation. So here you can see the 2 different seasons. This is winter, this is summer. Here you have the observation of mean precipitation, so total amount of precipitation, mean intensity, mean frequency, and the percentile 99 of heavy precipitation. If you look at the mean values from the RCM, you can see some kind of details. So for example, in winter, the mean amount of precipitation hasn't changed so much from the 2 approaches. The intensity is much higher is slightly higher on the high resolution models. Both models overestimate the frequency of precipitation, and they kind of do similar things for extreme precipitation and winter. On summer, the picture changes quite some. For me, daily precipitation is still not so different. The high resolution models tend to precipitate a bit more, but you get a much better approach in terms of precipitation intensity at high resolution, and then you also get an underestimation of frequency that corrects an overestimation that you have at 12 kilometers. And you can see that in terms of extreme precipitations in summer, the ensemble of high resolution models with split convection tend to behave much closer to the observations than the 12-kilometer counterparts. Okay, so I'm going to try to go slightly faster so we can finish on time. That was the results when you look at the mean of the ensembles, but if you look at every individual ensemble, the picture changes quite a bit. So you can see here the observations of the 99 percentile of daily precipitation. This is what the mean looks like, but if you look individually on each ensemble member, there is a huge spread. Of course, these values are closer than the 12-kilometer counterparts, so we get on average a better representation of extreme precipitation events with high resolution models. So that kind of hints that this is kind of like a much more physical approach, so to say, to this to representing this precipitation intensity. So then we might trust more the projections because we represent better the present day extreme precipitation events. But as I said, the spread between models is very strong. Now we move into early precipitation statistics. Here the picture changes a little bit because we enter into a more detailed comparison. Here what we get is the intensity, frequency, and heavy precipitation intensity for winter and for summer. And what you can see, for example, is that both models overestimate the frequency of precipitation in winter. It's still not very clear why. But when you look at summer, for example, the frequency of precipitation is strongly overestimated at the coarse resolution, and it gets much better improved when you move to high resolution simulations with explicit convection. Heavy precipitation similarly follows a similar thing. So the observations are shown here. Then you have the mean of the coarse models here is they underestimate strongly extreme precipitation intensity at hourly timescales, while it gets massively improved when you move into higher resolution simulations. And also for the mean precipitation, you see something similar. So high resolution simulations really improve the hourly precipitation statistics of the climate, basically over summer. Again, that was good if you look at the ensemble mean, but if you look at the individual ensemble, at the individual members, when in hourly precipitation intensities, this is the 99.9 percentile of hourly precipitation, you get also a huge spread in both 12-kilometer models and 3-kilometer models. You, of course, again, as when we look at daily precipitation, get a much better agreement of the 3 kilometers, so you might expect that the representation of this process is much more physical, so we should trust it more. But the spread between models is really, really strong. So you can see, for example, I think these are the WRF models. Some of them really underestimate extreme precipitation intensities. Some of the Cosmo model overestimated, although we have to say that the observations of extreme precipitation over mountainous areas are not very, you know, they might have some biases. They might underestimate the streams. But still, the spread is pretty strong, even at the high resolution. Here, what I'm showing is this matrix in which you have the different models, the different seasons, December, June, July, August. The top corner shows the bias in the different metric for the high resolution models, and the bottom one, the bias for the coarse models, right? So if you look, for example, at winter, and you look at the mean precipitation, you see that both for the high resolution models, the top corner, and the coarse resolution models, the bottom corner, you get an overestimation of mean precipitation in winter for all the models. When you move into the summer season, what you get is the opposite. So the WRF model, the WRF models that are here tend to underestimate mean precipitation, while some other models maybe do a bit better. You can see that, for example, for the percentile 99 and the intensity of precipitation over the summer, you get lower, in general, lower biases when you move from the bottom corner to the top corner. So basically, you get an improvement in the representation of precipitation, especially over summer and over autumn, for example. But there is a huge spread, and it's not always clear that you get a clear improvement, but we do like that. When we look at hourly precipitation metrics, we get more or less a similar thing, but perhaps the values are a bit more extreme, so to say. So looking at hourly precipitation metrics, all the models, both high resolution and low resolution models, tend to overestimate the frequency of precipitation in winter. We don't know why, also summer and autumn. And this bias on too much precipitation frequency tends to be corrected in summer when you move into higher resolution models. As I said again, these biases, for example, if you look here, this is too little intensity of precipitation over summer, tends to get much closer to the observations when you move into higher resolution precipitation. So overall, what we get is these two pictures. There are some metrics that don't change that much, or maybe they are the day and the night, so you have too wet, then too dry, and it's not clear that moving to high resolution helps us improve in that, but there are some other metrics in which you clearly improve the representation. That was Switzerland. This is the similar thing when you move into Italy or France. Maybe you can see more clearly, for example, in Italy, that the streams are much better represented at high resolution simulations than at low resolution simulations. It might be due to the fact that in Switzerland you have a strong orography that's somehow it forces the amount of precipitation, while in more plain areas that you don't have so much orography, the high resolution seems to be doing better. Okay, so this is pretty much, yeah, of course, the diurnal cycle. One of the points in which we get a lot of improvement is when we look at the diurnal cycle of summer precipitation. So here you get in black the observations over Switzerland of summer precipitation. The blue line shows the coarse models at 12 kilometers, and the red line shows the high resolution models. And you can see clearly how the peak of precipitation is much better on line with the observation. So we get a delayed peak of summer precipitation, therefore is a much better representation of convective processes that are the ones that produce this peak in the afternoon precipitation. For frequency and for heavy precipitation, you see the same. So there is an improvement by moving to high resolution. But if you look then at the spaghetti plot, if you look at the individual ensembles, the spread has not been reduced. So the blue lines, you see here a big spread in what every model produces. The red lines, you get a similar spread. There are even some models that don't really produce a good precipitation during summer. That is not very clear why they don't really produce that. So there is a lot of things to, and moving soon. So that was the diurnal cycle. If you move to France and Italy, you get a similar thing. Of course, the diurnal cycle of summer precipitation is not so clear in those countries as it is in a periodographic region, but pretty much is the same. So the spaghetti plot, you still have it at high resolution. And now the question is, why do we have that? Why we haven't been able to decrease the uncertainty if we were expected to have convection derived by the model dynamics that tend to converge. So my conclusions, in general, the spatial patterns of precipitation are represented quite well by the ensemble of kilometer scale simulations. In some cases, the kilometer models are better than the ensemble of the coarse models, especially over summer, but it's not always like that. The ensemble mean of kilometer scale simulations, some superior performance to reproduce the diurnal cycle of precipitation and also the streams. However, it must be noted that there is still a large spread, and we should try to understand why, even when we get rid of the convection and we go to the kilometer scale, that the dynamical course should kind of convert into how precipitation should be dealt, we still get this large spread. So there is a lot of things to do. And we should note that some of these models are run for the first time at this high resolution simulation, at this high resolution without calibration. So some of the results might be improved with a more detailed analysis. Thanks.
Thank you very much. Thank you. So we have time for one or two questions. Does Antje have a question?
Yes, I have a question. I was intrigued by the.
Can't hear you, Antje.
Can you hear me?
No.
A little bit, yeah.
Just, but not very loud.
I don't know. I try to shout. I was interested in the differences in your results between winter and summer, and I was wondering whether you can look at the convective part of the precipitation separately from the large scale part to understand these differences better.
Yeah, so that's a really interesting question. I mean, on the high resolution simulations, we use split convection, so we don't clearly have two output streams for convective or explicit. So everything comes from the microphysics. There's no way to separate it easily. But there are some people from Stefan Zablowski group who are trying to do a classification of different types of precipitation and see how these types change in the future. So there is some work going into that direction to try to understand what is happening in winter and in all seasons.
Thank you. And Sophie, on CNRS, IPSL, you have a question?
Yes, can you hear me?
Yes.
Yes.
Yes, it's not a question, it's a remark and a message for WP4. As you saw, the IPSL simulation presents a very strong dry bias in summer. And it is the same for BCCR, which uses also WRF, but we think that it's physically unrealistic, so we will have to rerun this simulation. And so I think it cannot be used for WP4 analysis. And but for the historical, it only concerns the run forced by ERA interim. For the historical and the future runs, we change our configuration, so it can be used for further analysis.